When theorists push a mathematical model of spacetime to extreme scales, it stops outputting standard physical predictions. Instead, the equations fracture and generate external structures, complex poles, Riemann sheets, and non-orientable topological surfaces. The math remains operational, but the output requires heavy quarantine to make any physical sense. For decades, mainstream theoretical physics has relied on a foundational assumption that the universe is built out of a local spacetime geometry. That presumption guides the vast majority of institutional cosmology and quantum gravity research. In 1908, Hermann Minkowski formalized a four-dimensional coordinate system that became the basis for special relativity. The effectiveness of this geometry created an enduring occupational hazard. Theoretical physicists began confusing successful coordinate maps with the final architecture of reality, a professional misconception known as the Minkowski tap. To bypass the limitations of a purely local flat geometry, contemporary researchers introduce complexified coupling constants, self-adjoint stactional kinetic operators, and higher-dimensional topologies. Under the TCGS-SEQUENTION framework, these mathematical structures are not undiscovered dimensions or physical mechanisms. They are symptoms of projection domain stress, places where the math breaks down because it is asked to carry ontological weight it cannot bear. A true source-level invariant describes reality regardless of the coordinate system used. A mathematical artifact, by contrast, is a byproduct of the specific geometry used to write the equation. When a map generates artifacts that must be filtered out to preserve physical meaning, the map has reached its limit. Because these formal failures are structural and recurrent, we can track them. We can establish a formal boundary grammar to diagnose exactly when a theory has overextended its cartographic admissibility. This diagram illustrates the baseline ontology required to run our audit. The complete, non-temporal source reality is represented at the top as 4D counterspace, or C. It projects downward to form the three-dimensional observable world, designated as the shadow domain, sigma. Every observable phenomenon in the shadow domain, the standard fields and geometry we measure, functions as a structural pullback directed directly from the higher source reality. By applying this projection model, we can audit three independent, highly cited theoretical constructions. In each case, a space-time first approach hits a dead end, forcing the authors to invent mathematical admissibility rules. Mapping this boundary grammar reveals a consistent pattern. The most exotic features of modern cosmology appear precisely where standard spacetime theories cease to justify their own existence. The first case study originates with a proposal by Juan Maldacena, Alexander Maloney, and Brian McPeak. They analyzed Euclidean gravity models coupled to massless scalar fields to study the formation of wormhole geometries. The formal mechanism requires continuing the scalar field values into imaginary directions. This mathematical step alters the stress tensor contribution, which is necessary to support the saddle shape of the wormhole. By pushing this continuation, the authors derived an upper limit on the displacement between asymptotic regions. They identified an imaginary distance bound, a cap on how far gravitational couplings can be analytically continued into complex space. This grid visualizes the trajectory of that formal extension. The path maps the analytic continuity across a complexified space, but it hits a hard limit at the imaginary distance bound. In our framework, we classify this exact collision as an analytic continuation boundary. Notice how the trajectory flattens out. The imaginary direction is an artifact of extending the math. The wormhole saddle is not a physical tunnel connecting coordinates in ontic time. It is the point where the projection ceases to be cartographically admissible. The authors explicitly link this distance bound to similar theoretical guardrails, including complex metric admissibility conditions and weak gravity constraints. The need for these mathematical walls signals a systemic breakdown across multiple quantum gravity models. If you attempt to calculate past this limit, corrections that were previously small explode in magnitude. The low-energy effective theory loses control and collapses. The mathematical spectacle of the wormhole captures attention, but the true scientific value is the hard admissibility limit. The boundary itself is the information.
The second case study addresses field theories attempting to implement multi-scale dynamics. Theorists achieve this by inserting self-adjoint fractional powers of the D'Alembertian operator directly into the kinetic equations. Fractional operators successfully generate a required physical mass mode. However, they simultaneously spawn unintended mathematical debris, heavily overproducing complex virtual sectors and branch discontinuities at the tree level. This visualization maps the Riemann surface of the operator's Grimes function. The mathematical map detonates into a chaotic field of unstable, complex conjugate poles, immediately ruining the physical interpretation of the theory. To prevent perturbative unitarity from collapsing, the authors rely on the Fakion prescription. This artificial quarantine mechanism explicitly boxes out the unphysical modes, ensuring they never enter the pole of asymptotic states. The severity of the quarantine depends entirely on the operator's parameters. Non-Hermitian and Hermitian sectors require different rule sets to force the equations back into compliance. We classify this failure mode as a spectral admissibility boundary. The mathematical syntax was altered, and the resulting mathematical excess had to be quarantined. Fractionalizing the kinetic grammar does not dig deeper into physical reality. It overproduces mathematical artifacts that theorists must manually strip away to maintain a coherent physical model. The third case involves a higher-dimensional cosmological universe. Brian Greene and his colleagues modeled a reality built from the product of Minkowski space and a non-orientable Klein bottle. By embedding this specific compact geometry, the authors recognize that the observable asymmetry in our universe cannot be explained using only local flat spacetime. Because the topology is non-orientable, fermions transported around the Mobius direction flip their chirality. This built-in geometric twist directly violates discrete charge and parity symmetries. This global topology enforces a background of fermion correlations, acting as a massive order parameter. When a three-dimensional brane travels through this localized condensate wall, the resulting intersection sparks particle production. With TCGS-SEQUENTION analysis, we categorize this behavior as a topological symmetry boundary. The authors recognized that the standard local description was insufficient to drive cosmological asymmetry. To solve the discrepancy, they bolted an extra non-orientable global topology onto the extended spacetime map. The condensate wall functions as a shadow-readable trace of a deeper admissibility constraint. It is a highly effective calculational tool, but it does not represent the physical discovery of a non-orientable extra dimension. This comparison identifies a clear logical pattern. The imaginary distance bound, the Fakion quarantine, and the condensate wall all reduce to identical constraint lines on the observable shadow map. If independent extensions of a theoretical map repeatedly require external analytic bounds, spectral prescriptions, or topological interventions to maintain physical meaning, the base map is not ontologically self-complete. To prevent future theories from falling into the Minkowski trap, this table applies a strict 5-level audit discipline. It forces researchers to isolate the raw mathematical structure from the source claim, compute the actual boundary, and finally extract the ontological critique. The framework relies on a strict no-absorption rule. It explicitly refuses to adopt fakions, wormhole saddles, or extra-dimensional branes as source-level machinery. These objects exist solely as external diagnostics. Executing this discipline requires a rigid distinction between different categories of measurement: an operational clock variable, a foliation index, and an imaginary mathematical displacement cannot be conflated without destroying the logic of the entire theory. When confronted with exotic calculations, the typical response is either a naive reverence for the complex math or a crude dismissal of the strange results. This boundary grammar provides a rigorous third path. The observable universe is simply a shadow domain. When physicists attempt to mathematically map the constraints of the higher source reality from entirely within that shadow, they will predictably hit boundaries. Theoretical physics produces rigorous, exquisitely detailed mathematical tools. We must retain those equations while completely rejecting the ontological inflation that accompanies them.